James Clerk Maxwell was an amazing physicist and an amazing Christian. If you ever have a chance to read some of his writing or even look up some of his quotes about God and creation, they are very profound and they are very devotional. He did not live very long, tragically. The Lord took him home at about the age of 48, and he had abdominal cancer. In 1865, which of course is the last year of the Civil War, he's of course is over in England, he makes some predictions or statements that revolutionize science in the 19th century, as well as provided the mathematical framework for explaining many of the physical discoveries that another Christian, Michael Faraday, made. Michael Faraday discovered these relationships, and he employed them in the manufacturing of motors and generators, but it was James Clerk Maxwell that explained it in terms of a theory of electromagnetic radiation. And there are several points to this. Point number one, electric field lines originate on positive charges, and then they terminate on negative charges. That's a convention. Number two, magnetic field lines always form closed loops. They don't begin or end in nothing, but they always start from some place where that creates them, and then they end someplace. The third one, a varying magnetic field induces a voltage, an EMF, and hence creates an electrical field. So in other words, there's this relationship between magnetism and electricity. And you studied this when you did the lab on Faraday's law and read about it back in chapter 20. The next point is that the reciprocal of this is true, or we could say the opposite, and that is that magnetic fields are generated when you have electrical charges that are moving through a wire or a charged particle just moving through space. And that, of course, is something we talked about back in chapter 19. Now, there are consequences of these four statements. The first consequence is that there are such things as what we call electric monopoles. Now, you never called them that. You called them positive charges and negative charges, or positive ions and negative ions. The second consequence is that because of these loops that always have to start and stop from something, there is no such thing as a magnetic monopole. In other words, there's no such thing as just a North Pole or just a South Pole, as far as we know. I will say, though, put a little asterisk here, that there are scientists who are still trying to figure out, is it possible to create just a North Pole or just a South Pole? Can something like that exist, perhaps at the quantum level? The third statement, we already said, is Faraday's law of induction, and the fourth is Ampere's law. And this is considered to be one of the greatest theoretical developments of the 19th century. In fact, I have the mathematical equivalent of each of these four statements on a t-shirt. And the front of the t-shirt says, "And God said." And then the back of the t-shirt has these four equations. Let there be light. Because one of the things James Clerk Maxwell demonstrated is that light is a form of electromagnetic radiation. And you'll see this word symmetric. James Clerk Maxwell, like many scientists, believed that in nature there is a fundamental symmetry, a balance, a form of beauty, that if one thing is true, something else ought to be true that's related to it. If moving electrical charges can create a magnetic field, then expanding and collapsing magnetic fields can induce moving charges in a wire. That would be symmetry. Or if you shine light on a metal, you can get electrons to jump off. Then if you shoot a beam of electrons at a metal, you might be able to get electromagnetic radiation to shoot off. In that case, we call them X-rays. So there's a certain symmetry that we expect to find. And he believed that. He felt that that was a function of the way in which a designer would create a universe. In a sense, you could say, without that phrase even being popular in the vernacular, that he was one of the early scientists who believe in intelligent design. He expected there to be this kind of symmetry, this kind of beauty. And you see that even in mathematics. Many times mathematicians will be working on some type of mathematical expression, and it gets messier and messier, and pretty soon they'll say, this is not beautiful. There's something wrong here, it's getting ugly, and they'll start over. But that symmetry says that fluctuating electric fields will generate magnetic fields, and fluctuating magnetic fields will generate electric fields instantaneously. So together we're going to call them electromagnetic waves. And they're going to travel at the speed of light. And because they travel at the speed of light, that means that all of these electromagnetic waves are a form of light. Or we could say that light is one example of an electromagnetic wave when we think about light as being something that is visible. And this is considered as one of the greatest discoveries of science. Now, in comes another scientist who also didn't live very long, who tragically died of an infection very early in his life, Heinrich Hertz, after whom we name frequency, a hertz, a cycle per second, an event per period of time. And the idea here is if you have a capacitor, two metal plates, and you also have an inductor would be nothing more than a coil of wire, a solenoid, a loop, in which you could have self-inductance. Oftentimes they put a metal rod, a steel rod, through the center of that loop in order to enhance the effect of the inductor. But assuming one or both of these things is already charged, as you open and close the switch, you can get the capacitor and the inductor, the capacitor to charge and discharge, and the inductor to have a magnetic field that expands and collapses very, very rapidly. In a sense, then, it would look something like this. I should come over to this page, excuse me. That the frequency that you generate will depend upon two things in this particular type of circuit. It will depend upon the strength of the inductor, which would be a function of the number of coils in the loop, as well as the diameter of the loop and whether or not there's a metal rod through the loop. And it'll be a function of the capacitor. And that would depend, of course, on the size of the two metal plates and how close together they are. And this equation actually is the equation we use when we want to select a radio or television signal out of the air and tune into it. We would call this, in a sense, the resonant frequency. That if we have this circuit and we adjust the inductor, and the way that you would adjust the inductor is by turning a knob, which would move the metal rod into and out of the coil to some degree, or maybe your knob is connected to a series of capacitors that are in series and would rotate the metal plates so that they overlap more or overlap less. Either one of these things would change what this resonant frequency is that your circuit would be tuned into and would look for in the air, in space. And that's how you would tune in your radio signal or your television signal on your TV or radio. And it's roughly analogous to the idea of having a whole bunch of pendulums. And if you start one pendulum going back and forth, and on that same tabletop you have other pendulums, only those pendulums with exactly the same length, and therefore will have exactly the same period, will begin to vibrate. You will have matched their resonant frequency. In a sense, the one vibrating pendulum will cause the other vibrating pendulum to vibrate. You could say that the first vibrating pendulum is kind of like the transmitter. that sends out a radio signal, and then the other pendulum of the same frequency or tuned into the same frequency will therefore begin to vibrate. That would be like the receiver. And this induction coil, which would be many, many loops of wire in a solenoid that's charged up, and it creates a wave of electrical energy that goes from the positive to the negative. It will actually create a similar effect on an adjacent circuit that doesn't have an induction coil. In any case, these kinds of investigations proved that because electromagnetic radiation displayed all the properties of waves like interference, diffraction, reflection, refraction, and polarization, think back to chapter 22 in our book, that therefore electromagnetic radiation is a form of light and also travels as transverse waves. Now, we can measure that speed of light, which we weren't always able to do until later in the 19th century, and to one significant digit, there's your speed of light. But of course, now we know the speed of light to many more significant digits than that. And you'll notice that later on that the speed of light depends on nothing except the medium through which it travels. And so, in other words, the speed of light in space is going to be 3 times 10 to the 8th meters per second, or 186,000 miles per second. And nothing can make that slow up or slow down or speed up. That's its speed. That is the speed limit of light in the universe. Even if you are traveling in a rocket, going very, very fast, and you suddenly turn on the headlights or shine a flashlight out the window, the maximum speed of light, regardless of the frame of reference, and this goes back to the chapter on relativity, or precedes the chapter on relativity, is always the same. It doesn't change. So, when we want to send out signals like KMOX radio, which is one of the largest radio stations in the country, sometimes you can pick it up on either coast. It's at 1120 on the AM dial, and what that means is that it has a antenna that vibrates charges at 1,120 kilohertz. Or if we talk about Joy FM, which is at 99.1 on your FM dial, does that at 99.1 megahertz. And that's how the antenna has to vibrate to send out that particular radio signal that can be tuned in by a car radio or a house radio or something like that. And this is kind of a diagram to show that happening at certain intervals of time, where we have our alternating current that is going to be creating an electrical field going in one direction and then an electrical field going in the opposite direction halfway through the cycle. And this is going to be in between, or 1/4 of the way through the cycle, and this would be 3/4 of the way through the cycle. In here would be 3/4 of the way. They don't show that picture. And then when we finally get over here, that's having completed one full cycle. We start and we end at the same spot. So whenever a charged particle accelerates, it's going to radiate electrical energy. It's going to create an electromagnetic wave. And that electromagnetic wave is a transverse wave with an electrical component, vector, that is at right angles to your magnetic field component. And both of these are mutually at right angles to the direction of propagation. And so when we come over here, we have a new right-hand rule. And this right-hand rule, looking at this picture right up here at the top, remember the green represents the magnetic field lines and the orange the electrical field lines. If you point the fingers of your right hand in the direction of E, and then you curl them in the direction, the shortest direction to get to B, your thumb will naturally point in the direction that the light is propagated. I don't like to use their right-hand rule. In my right-hand rule, I will have my fingers, like I usually do, represent the magnetic flux lines, and then the palm of my hand would represent the push that's making the electrical field, and therefore my thumb is representing the electrical field, just like my thumb often represents the direction of current in a wire. And that means that the palm of my hand is going in the direction that the light is traveling. You can try that right-hand rule or use the one in the book. Of course, it's not like the earlier right-hand rule where my palm represented the force that would act on a charged particle moving in a magnetic field. In this case, my palm is acting like something that's making the light travel in the direction that it's traveling. And once again, if we're going through free space, you'll notice that my speed of light doesn't depend upon anything that is physical. It simply depends upon mu and epsilon. Mu being the permeability constant of a vacuum, and the permittivity of free space is epsilon. But light always travels in space at a certain speed, and here you have that speed to 6 significant digits. Interestingly enough, the ratio of the electric field to the magnetic field gives us the speed of light. We're going to skip this section on the intensity of light and try to wrap things up here a little bit with, here we go, these conclusions at the bottom. In summary, number 1, electromagnetic waves travel at the speed of light. Number 2, electromagnetic waves are transverse waves. In other words, they've got a component that goes like this, up and down on this page, but also in and out. If this is the magnetic, then in and out would be the electrical. So we could say in, out, and so forth. And that's mutually perpendicular to direction that the light is being propagated. Number 3, the ratio of the electric field to the magnetic field equals the speed of light. And finally, the electromagnetic waves carry both energy and momentum, which can be delivered to the surface. And that's pretty remarkable in order to think about the fact that light, which is pure energy, can have the effect of momentum or pressure. And we know this, for example, because when light shines on the tail of a comet, a tail being a very condensed or amorphous, spread out kind of gas from the burning material in the head of the comet, it actually pushes that comet. So, for example, if this is the sun, and this is a comet that's going around the sun in an elliptical path, let's say it's going this way, the tail of the comet is always going to, and I'll use a different color for the tail. I'll use green for the tail. The tail of the comet is always going to be away. If the comet's right there, the tail is going that direction. If the comet's right there, the tail is going in that direction. If the comet's right there, the tail is going that direction. If the comet's right there, the tail is going in that direction. But the tail of that comet is always being pushed away by the pressure of light from the sun. And let make me positive I finished everything. Yes, that concludes this section of chapter 21.